Hello everyone, welcome to my YouTube classes. Here we are going to discuss on A-level physics. First of all, I would like to say sorry because for quite a long time I had not been able to uh, upload any contents on physics. So sorry, it is particularly not because of a very big reason, but kind of, little procrastination actually. So, well, I came back again. I will try to maintain that consistency. So, today we are going to start our discussion on stationary waves. Stationary waves can also be called as standing waves. So, as you understand that stationary or standing, it means that it is not the progressive waves. Progressive waves keep continuing, keep progressing, keep traveling from one place to another place. Here, the standing waves or stationary waves, this wave just gets confined in a given place, in a given region. So it is not being transferred from one place to another place. Rather, it is being trapped. It is being confined in a particular region. So this is a stationary wave, and here the actual stationary wave that we see, I mean the effect, the resultant effect that we see is basically the superposition of two waves that are moving opposite to each other. So when two waves move opposite to each other, they superpose with each other constructively and destructively. When constructive superposition takes place, the amplitude of vibration of the particle becomes maximum. When destructive superposition takes place between the two waves moving opposite to each other, the amplitude of vibration becomes zero or minimum. So that is standing wave, which is just particularly confined, trapped in a particular, you know, region. So it is not being transferred from one place to another place. It is opposite to the progressive wave. It is not same as the progressive wave. So here we would like to see in details about these stationary waves. So let's get started. First, we start with the difference between the progressive waves and stationary waves. So the first difference is that I already mentioned it. Progressive waves means the wave that keeps progressing. So it is a continuous process of flow of energy. So the energy is being continuously transferred from one place to another place. But when we say stationary wave, that means the wave is stationary at rest. And while it is at rest, it is at rest at that given point, that given position, from one end to the other end. Between these two ends, the wave is stationary, standing. It is not being transferred from one place to another place. So energy also is not being transferred. The first difference is in progressive wave, energy is transferred. In stationary wave, energy is not transferred, not conveyed. Rather, it is being stored or trapped or confined. The second one is that when we say the progressive wave, the one that I drew right here, transverse wave, and here we understand that some particle is at the maximum displacement, what we call as crest or trough. some particle is at zero displacement, what we call as in equilibrium, and there are some particles which are neither at equilibrium nor at crest or trough. But the particles, they all are going to be vibrating to that particular maximum displacement. The point, the particle which is right now at equilibrium, at next instant it will no longer remain at equilibrium. So at time it will go to the maximum displacement, what we call as the amplitude. So one of the basic characteristics of progressive waves is all the particles have the same amplitude of vibration, but obviously not at the same time, at different times. Right now, the wave that we drew here, some particles are at crest, some are at trough, some are at equilibrium. So the particles will keep on changing their position, but all the particles will ensure that they will have the maximum amplitude of vibration, but at different times. But in standing waves, there are some particular points, namely nodes, where the particles don't vibrate at all. So when you see the stationary wave, you will see that particular point doesn't vibrate at all. That point makes the particle not to vibrate. Why it is so, we'll be discussing it later, but the characteristic of the standing wave we have found here, that particles all are not vibrating at the same amplitude of vibration. When we see the resultant standing wave, there are some points, we'll call those points as nodes, and we'll see the particle not to vibrate at nodes. So this is another difference between the progressive wave and the stationary wave. The third one is that when we draw a progressive wave, we see that all the neighboring particles, they are not in phase. Neighboring particles are not in phase. Now, what is the criteria for the particles to be in phase? The particles will be in phase if they have the same displacement, same speed, and same direction of vibration. Now you just have a look on the progressive wave that I drew in my second point, and I marked 2 points with red color, showing that these 2 points are in phase. If the wave is traveling towards right, then these 2 points are in phase. They have the same displacement, means right here zero displacement, they are in equilibrium, and by default all the particles in a wave will have the same speed. And right here additionally, these 2 particles are going to have same direction of vibration. If the particle is moving, if the wave is moving towards right, then this particle is moving down, this particle also is moving down. So they have the same displacement, they have the same speed, they have the same direction of vibration. That means they are in phase. But the red mark point with the white marked point here, they are not in phase. These neighboring particles, they are not in phase. Why aren't they in phase? The first violation comes that they do not have the same displacement. So ultimately, the neighboring particles in the progressive wave, you will not see them to be in phase. Now here in stationary waves or standing waves, between two successive nodes, all the points are in phase. That means this is one node, this is another node. This is how the standing wave will look like. When you see the standing wave, this is how it looks like. You have already seen a demonstration in the lab how the stationary wave is being formed and how it looks like. You have uh, had an observation there that node is the point where particle doesn't vibrate at all. So between two nodes, these 2 points are nodes, all the particles here, they are in phase. This is superposition of the two oppositely moving waves, and when the two superpose with each other, here we have found some vibration of the particle, and this vibration of the particle, when we found, it means they two met each other in phase. So between two nodes, all the points are in phase. Between two successive nodes, all the points are in phase. X and Y, these are the neighboring points we can call as, and they are in phase. But right here, these neighboring points in the progressive wave, they were not in phase. So X and Y are in phase, U and V are in phase, but X and U or Y and U or V, they are not in phase. What we can rephrase or restate the point that particles at the either side of the node are in antiphase. They are not in phase, they are in antiphase, either side of the node. So X and Y, U and V, they are the either side of the node. They are in antiphase. So here I wrote it, X, Y, they are in phase, U, V in phase, but X, U, antiphase. Y, U, antiphase. Y, V, antiphase. X, V, antiphase. So these are the three major differences between the progressive wave and the stationary wave. All right. Now we are heading to form the standing wave in the lab, that the demonstration that you have just seen. So what did we do? Here we have a vibration generator which is connected with a variable AC power supply. Variable AC power supply from where we can alternate the frequency, and a string is attached at the end of a vibration generator, and the other end of the string is made to pass through a pulley, and it is here attached with a load, so that this part of the string from the vibration generator to the pulley, the string is as straight as possible, and we measured the length of the string. That is what we call as the effective length. Now, when at particular frequency the vibration generator vibrates, this causes the string to vibrate as well, because the string is attached with the vibration generator. So as the string vibrates, the disturbance causes the wave to be generated, and this wave travels down the length of the string. This is what we call incident wave. And as the wave travels along the length of the string, reflects back from the pulley. So this incident and reflected wave, they two superpose with each other constructively and destructively. So at the lowest frequency, when we made the string to vibrate, we see the loop to be observed like this. This is the loop we observe at the lowest frequency, what we call as fundamental frequency. Fundamental frequency is the lowest frequency when we see the pattern of the string to be like this. And the fundamental frequency is also known as first harmonic. So here you see the vibration generator and the pulley. These are the two fixed supports, two fixed ends. Two fixed ends, two rigid ends will always correspond to a node. So here at the vibration generator, we see the node. Here at the pulley, we see the node. And at the lowest frequency, as we understand what is the definition of frequency, frequency is number of wave being produced per second. Lowest frequency, lowest number of wave we will see. And the shortest wave that we see right here on the string at this lowest frequency, the pattern has to be a rhythmic pattern. No irregular pattern will be called as standing wave. So this pattern you will see at some particular frequency, not any random frequency. So ultimately, this pattern gives us an understanding the lowest wave being produced, and this wave is not even a single wave, it is half of the wave. And this half of the wave has been fit in this length of the string. I mean on this length of the string. So this lambda by 2 equals to the length of the string L. When we subject lambda, it is twice L. So how much is the wavelength? Twice the length of the string. And what is the length of the string? The length from the vibration generator to the pulley. All right. So this is one loop we get. These are the two nodes we get. In between two nodes, A stands for antinode. Here the particle will have largest amplitude of vibration, maximum amplitude of vibration. What would be its amplitude of vibration? If these two incident and reflected waves have the same amplitude, then here in antinode we will see the amplitude to become double. 2 and 2 becomes 4. Why is it so? Because antinode is the point where the two waves meet each other constructively. And why does the constructive superposition leads to a maximum amplitude of vibration? Because constructive superposition takes place when two waves are meeting each other in phase. When they two meet each other in phase, that means crest is overlapping with the crest, trough is overlapping with the trough. So they are going to reinforce each other. So if the amplitude is, that means maximum displacement from the equilibrium position to the crest or from the equilibrium position to the trough, if it is 2 centimeter, when crest and crest they two are overlapping, 2 and 2 are overlapping in phase, it is going to reinforce the wave amplitude, reinforce the wave particle vibration. So this is why 2 and 2 becomes 4. Here in antinode, we see the largest amplitude of vibration. What happens to the nodes? Nodes are the point where destructive superposition takes place. The two waves, they meet each other in antiphase, so they cancel out each other, and here we see no vibration. All right. Now we are going to see the variation of the frequency. If we vary the frequency, how the standing wave pattern varies. So this is F1, which is just immediate higher frequency than the fundamental mode of vibration, fundamental frequency, immediate higher frequency, for which we get the loop to be like this, the standing wave pattern to be like this. And when this is F1 greater than F0, we see this pattern. That means here are, I mean, in first fundamental mode of vibration, there were 2 nodes. Now here would be 3 nodes. The nodes number is gradually increasing. At that immediate higher frequency, that means more wave is now going to be fit on this length of the string. Earlier we have seen half of the wave to be fit here. Now we see one complete wave to be fit here. But length of the string remains the same. Why is it so? Because we did not change the position of the vibration generator and the pulley. So length remains the same. In this length of the string, one particular wavelength that has been fit. So when we subjected lambda, we can say, which is just the length of the string, but in other words we can say it is twice L by 2. Why did we say twice L by 2? Because we are going to compare the wavelength, how much it has been decreased from the initial. So in initial phase, like in first harmonic, lambda was twice the length of the string. Now it is half the length of the string. All right, I mean it is half the length of the twice L. So when it was twice L initially, now it is half. That means lambda has been decreased and lambda has become half of the initial. So if lambda is half of initial, what the frequency should be? It is inversely proportional. If lambda is half, that means frequency is double. And here we have observed that this second harmonic, what we call as first overtone, has to be twice the fundamental frequency. That means if you observe this loop at kind of 10, frequency, 10 Hertz frequency, then you are not going to see the two loops at any other frequency except 20, because 20 is the twice of 10. So if you are observing this at 10 Hertz, you must be observing this pattern of the wave at 20 Hertz, no other than 20 Hertz. Not even 19 Hertz will enable you to observe this one. So second harmonic has been found as the 2 times of the first harmonic. Now we kept on increasing the frequency. Let's see what we see. If we increase the frequency, now F2 is greater than F1, so frequency has been increased, more number of waves are being produced, that waves are going to be fit in this particular length of the string. So initially we have seen half of the wave, then we have seen one complete wave, and now in this third harmonic we see 1.5 wave to be fit here. Length of the string remains the same. So 1.5 wave, that means length equals to 3 lambda by 2, so lambda equals to twice L by 3. So how much lambda has become compared to the first value, which was twice L? It is 1/3. So since lambda has become 1/3, obviously the frequency has become 3 times, and that's what we see. In terms of the fundamental frequency, the third harmonic is 3 times of that. Fundamental frequency has also been known as first harmonic, second harmonic, third harmonic, second harmonic again called as first overtone, and so on it goes on. So what we see here is, if we keep on increasing the frequency, the number of nodes and antinodes will be increasing. That means lambda value will be decreasing. All right. So if frequency is increased, number of nodes and antinodes increases too, so wavelength decreases. And what we have got as the pattern, between two fixed ends, harmonics are found at every F0, twice F0, thrice F0, 4F0, 5F0, and so on. And so on. These are we call as harmonics. First harmonic is at F0, second harmonic is at twice F0. So if it is at 10 Hertz, then 20 Hertz, then 30, then 40, 50, 60, 70, and so on. Integral multiple of fundamental frequency. So the harmonics are found at every interval of integral multiple of fundamental frequency. When? If the standing wave is being formed between two fixed ends. So just to let you know that we can form the standing wave in 3 different categories. One is the standing wave is being formed, is possible to form between two fixed ends. It is possible to form one fixed, one open end, and it is also possible to form between two open ends. All right. Distance between two nodes equals to distance between two antinodes, which is lambda by 2. Distance between node and immediate antinode is lambda by 4. So here we have seen just the standing wave between two fixed ends. Repeated constructive and destructive superposition takes place. Constructive corresponds to an antinode, maximum amplitude of vibration. Destructive corresponds to a node where minimum or zero amplitude of vibration what we see. All right. So the other things, that one open and one closed, between two open ends are yet to come.